Have you ever thought about the universe and asked perhaps the most profound question of all, where did all of this come from? For as long as humans have been around, we've not only asked these questions, but have provided stories, based on logic, reasoning, mythology, religion, and many other avenues, that allege to give an answer. Although these stories remain popular and part of human culture even today, they don't provide any satisfactory solutions by the one criteria that matters most. Can they explain what actually exists within the universe in a scientific, reproducible way that yields accurate predictions about what we observe? We didn't have enough knowledge to apply that scientific approach to the entirety of the universe until the early 20th century, and as a result, we had only assumptions to rely on about our cosmic origins. Many assumed, as Einstein did, that the universe was static, unchanging, and eternal on the grandest of cosmic scales. But physics and astrophysics would soon point to a different conclusion, that the universe had a birthday, and the moment of its birth was the ultimate cosmic creation event, the Big Bang. Now, here in 2025 we've gone far beyond that initial idea, to the point where we now assert that the Big Bang wasn't even the beginning at all, but was preceded by an even earlier stage known as cosmic inflation. If you wanted to know where the universe came from, scientifically you'd be compelled to do two things. You'd have to learn the laws of physics that govern the universe and become adept at using them to calculate how physical systems evolved over time under those laws. You'd have to look at the universe itself in gory detail, revealing observable, measurable properties that you could use to tie what we see to the underlying physical theories that describe the full workings of our overall reality. For the laws of physics, that meant using Einstein's general relativity, a new theory of gravity, put forth in 1915, that swiftly superseded and replaced Newton's law of universal gravitation in describing our universe. You'd also have to go out and measure important properties of the universe. Up until the 1920s, we didn't know what the universe even was. Was it solely confined to the Milky Way and everything within it? Or were some of the objects we were seeing outside of the Milky Way, extragalactic objects or even galaxies like our own in their own right? A key measurement arrived in 1923, when Edwin Hubble was using a new telescope, the world's largest and most powerful at the time, to track the flaring of lights inside the Great Nebula in Andromeda, Messier 31. After observing 3 flaring events that he had labeled N for nova, he found a fourth in the exact same location as the first. In many ways it was the most important observation in the history of astronomy. Hubble swiftly realized that this couldn't be a nova, as it recharged or rebrightened far too quickly. Instead, it must have been a variable star, a special class of variable star known as Cepheids. But there were 2 other pieces of information associated with this, and Hubble, and others, used them to great effect. First off, Cepheid variable stars had already been investigated, studied, and sorted by Henrietta Swan Leavitt, who had established a relationship between the period of brightening and faintening of a Cepheid variable star, and the intrinsic brightness or luminosity of such a star. This relationship was profound, and it allowed anyone who measured the period of brightening and faintening of such a star to know how intrinsically bright it was. When we folded in how bright that star appeared, or its apparent brightness, we could then determine how far away that star, and hence, the galaxy it was needed to be. We also had the ability to measure how fast the host galaxy for any star, even a variable star, was moving along our line of sight, either towards us or away from us. In the case of Andromeda, it was moving towards us, but in the case of nearly all other galaxies, particularly galaxies now known to be outside of our local group, the overwhelming majority of galaxies are moving away from us. Moreover, when we took data for a bunch of Cepheid variable stars in a bunch of different galaxies and began measuring their speeds, we saw a fascinating trend. The farther away a galaxy was from us, the faster it appeared to be receding. When we go back to Einstein's theory of gravity, this has profound implications for our universe. You see, in the framework of general relativity, you cannot take a universe, fill it uniformly with any species of matter or energy, and expect it to remain static and unchanging. Instead, such a universe will be compelled to either expand, with gravity attempting to pull things back together in opposition to the expansion, or contract, with gravity winning the war and drawing not just matter and energy but space itself, all back together. The observations from Hubble and others, in fact, settled this issue in the one way that matters: observationally or with direct measurements. It was now clear that the universe was expanding, and that the reason more distant objects were observed to be moving away from us more quickly than closer ones was simply because they were farther away, and the entire universe was expanding. A good analogy is to picture a ball of dough as the fabric of space, and the raisins all throughout the dough as the various bound structures, that is, galaxies and groups clusters of galaxies, found in space. As the dough leavens, it expands. Although we can't see the dough, we can see the light from the individual raisins within it. The more expanding space the light has to travel through in its journey to our eyes, the greater the stretch, or redshift of that light will be, explaining why these objects all appear to be moving away from us. In other words, the universe is expanding. So what does this mean for the distant past, or even more profoundly, for our ultimate cosmic origins? Believe it or not, these puzzle pieces were first put together all the way back in 1927. When only very early data from Hubble was available. Moreover, it wasn't Hubble, nor was it Einstein, who put these pieces together. It was Georges Lemaitre, as well known for being a Catholic priest as he was for being an astrophysicist. Lemaitre reasoned that if the universe were expanding today, and expansion stretches the wavelength of light that's within it, then the universe in the distant past must have been smaller and full of shorter wavelength, that is, hotter radiation. We can extrapolate even farther back, to an even smaller, hotter state. At some point, it would have been too hot to form even neutral atoms. At some even earlier point, it would have been too hot to form atomic nuclei. Even earlier, it would have been so hot that we couldn't form protons and neutrons, and instead would have a quark-gluon plasma. Even earlier, it would be so hot that matter and antimatter would have been created in equal amounts. Lemaitre imagined going to such a hot, dense state that all of space and all the energy in the universe would have been concentrated into a single point. This idea, of a singularity, would correspond with the birth of space and time itself. Lemaitre called this idea the cosmic egg. Others, like George Gamow, would later call it the primeval atom. Today, on account of a detractor of this theory, Fred Hoyle, we know this event as the Big Bang. It states, quite simply, that the universe was born with space, time, and all of the matter and energy within it emerging at once, with a rapid initial expansion. And as the universe expands, it also cools, with matter and antimatter annihilating away, leaving only a tiny amount of leftover matter, with quarks and gluons eventually forming into protons and neutrons, with protons and neutrons eventually fusing into the first atomic nuclei in the universe, with atomic nuclei eventually binding together with electrons to form the first atoms, and with those atoms eventually gravitating and clumping together to form stars, galaxies, and the grand cosmic web. Today, billions of years after the Big Bang first occurred, here we are. Humans, intelligent beings, have emerged and are capable of reconstructing that story. Along with it comes our entire cosmic history. At least that's the story. But is it true? To find out, we had to tease out observable predictions of this theory. The last 3 points in the above story would lead to 3 of the 4 cornerstone predictions of the Big Bang, with the expanding universe being the 4th, having already been firmly established. Those 3 observable predictions are a specific set of abundances for the light elements, deuterium, helium-3, helium-4, lithium-7, and more, that were forged in the early stages of the Big Bang, well prior to the formation of any stars. A leftover glow of radiation, black body in nature, that has been redshifted and stretched to extremely low temperatures by the cosmic expansion, where it should be only a few degrees above absolute zero by now. And a universe that exhibits hierarchical structure formation where galaxies are larger, more massive, and more evolved today, as well as younger, bluer, less massive, and more pristine at great cosmic distances. Although we see strong evidence for all of these today, it was the leftover glow of radiation, the cosmic microwave background, CMB, that proved the Big Bang. Its discovery, and then its measured properties, convincingly confirmed the Big Bang picture of our cosmic past while ruling out all other alternatives. To date, no alternative theory can explain the 4 cornerstones of the Big Bang. It stands alone, unchallenged, as the story of our cosmic past. But it can't explain everything. The Big Bang also has some unexplained puzzles within it. 3 big ones identified during the 1970s were as follows. If the universe began with a hot Big Bang, then how did different regions of sky, places where no cosmic signal at the speed of light could have exchanged information or heat between, know to have exactly the same temperature and properties, as seen in the CMB? If the universe began expanding, With gravitation opposing the expansion, then how did the expansion become so perfectly balanced that the universe never recollapsed or expanded so quickly that no structures could form, as shown in the illustration below? And if the universe achieved arbitrarily high, hot temperatures, then where are all the leftover high-energy relics predicted by all sorts of extensions to our physics theories? Things like magnetic monopoles? In other words, how did the universe know to be born with the specific properties that it must have possessed, when there's nothing mandating that it must have possessed those properties? In physics, this is an example of what we call a fine-tuning problem, where if the properties it began with were slightly different, the properties we'd see today would have been vastly different. In cases like these, what we search for is a physical mechanism that could explain why it has these particular properties and not any other. If it's a good physical mechanism, it will also produce novel predictions. Predictions that we can go out and test directly by making further observations. The proposed mechanism for a solution, first put forth in 1980 by Alan Guth, is known as cosmic inflation. Instead of beginning with a hot Big Bang, inflation states that an earlier state preceded it, one where all the energy in the universe was bound up in a different form, inherent to the fabric of space itself. This causes space to expand relentlessly and exponentially, doubling and redoubling in size again with each brief instant that elapses, for as long as inflation endures. This means that all different regions of space, even apparently causally disconnected ones, would have the same properties everywhere. As they originated from the same inflationary region, the expansion rate and the energy density of the universe perfectly match, because the energy density during inflation determines the expansion rate, and there are no leftover high-energy relics because the Big Bang never got infinitely hot, but rather only got as hot as the energy density during inflation would have allowed. In other words, all three of the major puzzles with the Big Bang, in its original form, are solved by the idea of cosmic inflation. That's very compelling, but remember, to overthrow an old scientific theory and replace it with a new one, we need to make novel predictions that we can go out and test. Fortunately, inflation has these in spades, largely because of quantum physics. If the universe is quantum in nature, then inflation must be a quantum field, and quantum fields fluctuate. During inflation, these fluctuations get stretched across the universe, becoming the seeds for both density fluctuations and gravitational wave fluctuations that our universe gets born with once inflation ends and the hot Big Bang begins. This leads to 7 unique predictions. The spectrum of initial density fluctuations should be almost but not perfectly scale invariant, and instead will be just a few percent larger on large cosmic scales than small ones. Those density fluctuations shouldn't be limited by the distance light could have traveled since the hot Big Bang, but should exist on larger super-horizon scales, as inflation can plant seeds on those scales. Those density fluctuations should be 100% adiabatic in nature, and 0% the alternative, isocurvature. We should observe a maximum temperature, imprinted in the cosmic microwave background, that the universe could have ever achieved after the end of inflation, one well below the Planck energy temperature. We should see tiny departures from perfect spatial flatness to the overall universe, somewhere between the 0.0001% and the 0.01% level. We should observe a primordial spectrum of gravitational wave fluctuations, whose spectral shape is determined by inflation, but whose amplitude is dependent on the particular model of inflation. And we should observe a universe whose fluctuations are almost perfectly Gaussian or normally distributed in nature, with exotic alternatives producing large non-Gaussianities. Of those 7 predictions, we've sufficiently tested the first 4. Inflation is 4 for 4 and the non-inflationary hot Big Bang is 0 for 4. That's a slam dunk, a smoking gun for inflation, and an overwhelmingly convincing scientific test all at once. The level of profundity of the implications of all of this cannot be overstated. It means that the Big Bang wasn't the beginning of the universe, but rather was preceded and set up by cosmic inflation. Inflation isn't some speculative idea that hasn't been tested. It's cleared all 3 of the major scientific hurdles that any new theory must clear to become accepted. It's reproduced all of the prior successes of the earlier prevailing theory, the hot Big Bang. It solves the 3 major problems, the horizon problem, the flatness problem, and the monopole problem, that the earlier theory, the Big Bang, couldn't address. And it's made a suite of novel predictions that are both in principle and in practice testable, and of the 4 critical tests that have been performed, The new theory is 4 for 4, while the old theory is 0 for 4. Meanwhile, future experiments can continue to probe the remaining, insufficiently tested predictions. Future missions probing small-scale fluctuations in the light and the polarization of the cosmic microwave background can continue to lower our constraints, presently down at the tilde 1% level, on the level of its departure from perfect flatness. Those same classes of experiments as well as pulsar timing data can constrain the spectrum and amplitude of gravitational wave fluctuations. And all-sky galaxy mapping missions, such as the new Sphere X mission, can probe non-Gaussianity to the most sensitive levels of all time. The goal now isn't to confirm inflation, we've done that. The goal at present is to learn more about what the properties were of the inflation that occurred in the universe, to investigate what preceded and set up inflation, and to find out whether our universe truly did have a beginning way back, before our observations can give us any meaningful information, and what that initial state was like. The Big Bang still plays a major role in cosmic history, but it wasn't our ultimate beginning. Instead, cosmic inflation preceded and set up the Big Bang, and unfortunately for us all, the signals from inflation that are imprinted on our universe correspond to merely the final tilde 10 circumflex 32 seconds of inflation. What came before it? That's the new question we're still trying to answer.